Hello, it's Keith here, and this is lesson 8 of the YQuest code for the 6502 systems. We're going to be looking at the VIC20 today. We're going to look at the platform-specific code that makes up YQuest. So if we just give YQuest a quick go here. So this is the YQuest on the VIC20, and we're using the characters. We're using custom characters here to do the graphics, obviously. And you can see it's basically the same game, just on a little bit smaller screen. Now, we're using the text that we used on the Atari Lynx, so you can see lives has been shrunk down to LI and so on, but it's basically the same game. Okay, so that's the game, and we're going to be looking at the code that makes up the VIC20 specific version. There's the common code, of course, which we've covered before. Let's go over to the source code and let's have a look at what makes the VIC20 version tick. Okay, so here's the code. Now, the first thing that you see on a lot of these systems that use a tile map, or what is effectively like a tile map on the VIC20, is these collision masks. On the sprite systems, on the systems with bitmap graphics, we would potentially have graphics that overlap, and that is calculated internally. But on this system, we're not representing the calculated X and Y coordinates as accurately as we'd like on the screen. And so to make sure the collision detection matches what's shown, we're reducing the resolution of the collision detection with these here. Here's the size of the screen for the various logic routines. We've then got some common macros. We've got the Z registers here, which are my fake Z80 registers that I use for a lot of my common code. User RAM, which is the game variables, and sprite pointer here. This is used by the sprite routines to calculate the color, because of course the different sprites are different colors. So we'll see that later on. We're starting as a cartridge here. We've got a cartridge header here, and we've got the program start here, which is the main code. The code is starting up the screen here by transferring some settings. This is all the same as in the simple series, so please take a look at that. Here we're transferring the tiles, we're calling them tiles, they're actually characters, into the custom characters here. We're then resetting the game RAM, zeroing it. And here's the start of our game. We're just resetting the lives and the level, things like that, clearing the screen, and then we're showing the title picture to the screen. Now we load in each tile number. There's one tile per byte in this definition of the title picture, and we're using getSpriteAddress to calculate the offset within the character map effectively, and then we're showing it to the screen with this routine. We'll see those later on. Now we repeat until we've drawn the entire tile map to the screen, and then we're just drawing some text to the screen, the high score message, the website, things like that. Nothing too exciting. We wait for a fire button to be pressed, clear the screen. We reset the player settings, moving back to the center of the screen, and we initialize the level with the objects thing, everything that the level definition uses. Now this of course runs at the start of every new level as well, not just the start of the game. We've then got a delay here. We've got two delays. The screen's so small and the graphics are so simple, it's a bit too fast, so we're slowing things down with these. If you reduce the size of these, you'll make the game faster. Here X is used as our buffer for any key presses. We use this routine to read in the joystick, and we store any changes to X here, and we're going to process those later on. Okay, now here we're drawing the text to the screen, the remaining lives, the score, the level, the crystals you've got to collect, things like that. We're then loading zero page entry IX with player object, and this points to the object that controls the Y of the player. We're then going to remove that from the screen before processing the directions. Now, when we press a direction key, we're actually changing the acceleration of the player. Now, because holding up would potentially make you accelerate too fast and you'd lose control, we have a timeout. If the timeout's non-zero, we skip over the rest of the direction processing. Direction processing works like this. We check each direction and we change the acceleration defined within the player object. So IX is pointing to the player object, and we set Y to the offset to the attribute within that player object of the Y acceleration or the X acceleration. Where is it? There it is. And then we're using these inc IX offset by Y or dec IX offset by Y to change those relative accelerations depending on the direction. If fire is pressed, we run the fire button routine. That's in the common code there. On two button systems, we've got a stop movement option, but that's disabled on this one because we've only got one fire as it's set up. Now we've got here, we're updating the key timeout, which has been set if any direction key's been set. And then finally, once we've done that, we run draw and move, which is the common code which handles all of the updates for the level, the moving of the enemies, see if the player's won, that kind of thing. See if they've died as well, of course, not so good. And inf loop jumps all the way back up here. This is the main loop of the level. Here's the clear screen routine. This is just wiping out the tile map, or the character map, maybe I should call it. I tend to think in tile maps. and here's our print character routine. Now it's a little bit tricky, but basically what it's doing here is it's calculating the offset from an X and Y position. It's then taking the current character and it's converting ASCII into the format that VIC20 uses. VIC20 doesn't use an ASCII layout, and also they're offset by 128 because of our definition of custom characters. Now we're then actually storing the newly defined character at the XY position calculated on the screen, and then we are setting the color at the respective offset and setting the color to 1, which is white, and that's drawing the character to the screen. Now that's the character drawing routine, but of course the sprite routine isn't so different really. Here's the blank sprite routine. We're loading the collision program from the object passed in IX. If the collision program is over 250, 254 is a dead object, 255 is a never used one, so we wouldn't draw that, otherwise we're doing the blank. And we're using the space character, again offset by 128, and we are using character 32 here, and that will remove an object from the screen. Get sprite address is calculating the address of the sprite within the characters, the custom characters. So first what we're doing is we're storing the sprite number in the sprite pointer here, and we need that for the color offset later. And then we are taking the sprite frame, because there's 16 sprites per bank and there's 4 banks, so this is the 4 frames of animation, multiplying it by 16 and adding that to the sprite number that we want to show, and that will calculate that in H here. Do get sprite object will show a sprite from IX, the object IX, get the YX position, and we also get the sprite number here, so that will show that to the screen. And here's the show sprite routine that does all the work. So we're getting the sprite number we want to show here. We're then calculating the XY position within the character map, the tar map, and then we're transferring that character number to that position in the screen. We're then offsetting to the respective color RAM, which is at 9600, which is offset by 7800 from the character map. We then load in the sprite palette offset by the sprite pointer, and we load in a byte there, and we store that to that calculated color RAM address here. Get VDP screen pods again is effectively calculating the screen RAM address of a character on the screen. There's 22 characters per line in this screen layout, so we're multiplying the Y position by 22, adding the X position, and that is effectively the resulting address. This is a very crude calculation here, but speed was not an issue for this game. When we want to read in the joystick, we're first having to set port B with this configuration here to define it as a read port. We're then reading in the joystick from 9120 here, the fire button, and then we're reading in up, down, left and right from 911F here. Now we're going to be shifting these around into the common format used by my main tutorials here just for convenience, and then we store it in ZH here. Now we use this as in our main code of course, but also for wait for fire. Wait for fire waits for the fire to be pressed down and then released, so it's used in for a level switch or for game over when the player may have been holding down fire for other reasons. And what we do is we're just re-randomizing the seed and then wait for that fire button to be pressed and released here, and that will work very nicely. Here we've got some common code. These are various bits that have been covered before. Chibi Sound was done in the platform specific series. Basic functions I use in all of my stuff, and show decimal was actually something I was working on for Chibi Aliens. So there we go. Now here's the 4 banks of bitmap data. These are the 4 frames of animation for each of the 16 sprites. There's no font for this version because I can't redefine that many characters, so we haven't done that. And here's the palette for the 16 sprites. There's only one palette, there's not one palette per bank. It didn't make sense for this game. And then finally we've got the VIC screen settings here, which define all of the settings of the screen, including the custom character definitions and the screen position, things like that. And that's really all there is to it. So there we go. So this is YQuest. It's very similar in some ways to the Grime. A lot of the ideas were taken from the Grime thing, but I think it might be interesting to you if you're looking to create your own little game and you want something to start from. As I always say, you're welcome to go to my website. In fact, I encourage you to get the source code and make it into a game of your own if it will help you. And I've said before, you're welcome to do that. You don't need to give me credit for it. And if you somehow sell it, then best of luck to you. You deserve all the success you get. So anyway, if you've liked this, please like and subscribe. Liking the videos makes YouTube recommend them more, and subscribing, it gives me more encouragement to do more work. So helps all of us. Anyway, whatever you do, I wish you all the best of luck with your programming projects, and I hope you have a lot of fun with them. Thanks for watching today, and goodbye.